Hello, I'm Professor Peter Challenor in the Maths department, and I'm interested in how data can be used to look at complex numerical models and how we can make decisions with those models. The world's facing a number of crises. One is climate. We're changing the climate, and we need to know how we're doing that, and we need to know what we can do to change that. But it's not only the climate crisis, there's also a biodiversity crisis, and of course there's the pandemic. And one common thing about all these problems is that we have complex numerical models that enable us to predict the future from the present day. Those models are very expensive to run. They need the biggest computers in the world, and they will take hours for a single run. Now that means that we cannot afford to do a lot of runs. Now those models are deterministic. If you run them twice with the same inputs, you get the same outputs. But we're never sure about the inputs. There's uncertainty on those inputs, and that gives us uncertainty on the outputs. And we're not sure about the structure of the model either. Our models are wrong. They're not the same as reality. And if we're going to use them to make decisions, we have to take that into account. So the classical way of solving the uncertainty problem would be what's called the Monte Carlo method. We'd sample from the probability distribution of the inputs, and that'll give us the probability distribution of the outputs. But to do that, we need to run the model thousands of times. And if they take 6 hours to run, you can't do that. That's where I come in. What we do is we build what are called emulators or surrogates of the model. So here's an example. There's the model, just one input and one output. I'm just going to run that 4 times at those 4 dots. And then I'm going to build, using some statistical machine learning type methods, what I'm going to call an emulator. And that red line is the expected value of that emulator. It's a probabilistic thing. And the dotted lines are the uncertainty. So it's exactly right where I've run the model, but it's not exactly right everywhere else. But if I now put the model, the true model back on, you can see it's a very good approximation. So it approximates the model, but it gives us a measure of its uncertainty, so we can take that into account. So given we've got this surrogate model, this emulator, we can now do things like predict the model in places we haven't seen before. We can do a sensitivity analysis, see which inputs to the model are important, and we can do the uncertainty analysis by doing that Monte Carlo calculation I talked about before. This now takes less than a second on a laptop as opposed to 6 hours on a big computer, so we can run this thing thousands and thousands of times. So the next thing we want to do is to calibrate the model. We want to take some observations. There's some observational systems there. And we want to make sure that the model agrees with those observations. We don't want a model that's a model of Mars when we're modeling the Earth. So we want to calibrate the model. And here's an example of calibrating a model. And the method we're using here is called history matching. And we calculate a thing called implausibility, which is a scaled distance from the model to the data. So we scale it by the uncertainty. So we rule out inputs that are too far away from the model. But if they're very uncertain, we don't know that they're too far away, so we don't rule them out. So here we've got a region at the left that's not ruled out and a region at the right that's not ruled out. Now we focus in and we do some more runs in a carefully designed way, and we reduce the uncertainty on the left, and we reduce the uncertainty on the right, so the left gets ruled out, but the right-hand side is not ruled out because now it's only the data uncertainty that's driving the region we can't rule out. So that's how we could calibrate a model. One of the important parts of the whole process is design. So one of the things we want to do is what are called space-filling designs. We want to fill space with as few points as possible, because every point costs us an awful lot of money. So here's an example of filling a 2D space. You will see it's not at all regular, because we just want to fill space as well as we can. Recently, we've been looking at methods to go beyond that. So you start off by filling space, and then you put new runs in places where you think it's going to be the most informative. So here's 4 different methods of doing that. Ours is in the top left. And the black points are the original points, and the red points are the points we add afterwards. Sometimes we're not just interested in an input and an output, we're actually interested in the dynamics of the model. And this is a famous example of dynamical system. This is the Lorentz butterfly, a chaotic system. And we've been working on methods for doing what we call dynamic emulation, where we actually emulate how these points go around that butterfly. It's a 3D version. And we do very well until we get into the middle of the butterfly, and then it gives up. It gives us huge uncertainties because you can't predict beyond that point. That's where chaos cuts in. So, are the models going to solve our problems? No, they're decision support. So, the models are never correct. They're always uncertain. But if we can quantify that uncertainty, we can give decision makers, we can help decision makers make decisions. Without the uncertainty, it's very hard to balance one model against another. And we have to always acknowledge that the models are models and they're not the real world. So thank you very much for listening. I hope you enjoyed it, and thanks again.